or fiber-based communication in this particular program as well. So the way I want to actually make this particular talk is that I will briefly first introduce you what are the quantum technologies and how they have been so famous nowadays. What was the reason that why people actually move from classical technologies to these kind of quantum technologies? And later on, I will also try to focus what are internationally being done in the framework of free space and satellite-based quantum communication, and what we have been doing, in fact, what the National Quantum Mission is actually doing in India. And then also I will try to touch upon what are quantum networks and how can we use free space based communication technologies along with fiber based technologies to develop these quantum networks, which ultimately would lead to quantum internet, which is very similar to the classical internet. And I will try to also briefly focus on that. Okay, so let us go back to 2 centuries before, somewhere at the end of 19th century, and see that at that time what was the situation. There was no quantum physics. There was only classical physics, and it was very much developed. There were many researchers who have contributed significantly toward the solutions of the existing problems. And in fact, the scientists by the end of the century were of the opinion that all bigger problems or major problems are already solved now. There is no physics problem remaining which we need to solve. And then there were certain questions which were still there, and classical physics was not able to answer them. They include the first thing is about black body radiation, because the black body radiation was not solved with classical physics. And then the light interaction with matter, the way classical physics or the nature of light, the wave nature, the particle nature at that time, which was corpuscle nature of Newton, they were not actually making us understand how the interaction of light and matter is happening. And then there were people like Einstein, Max Planck, and further Heisenberg, Schrodinger, Born, and many more, who contributed toward a understanding of these problems, solution of these problems. And that led to a completely new kind of physics, which is called quantum physics. And it has developed 1 century before, that is almost 100 years before, which now we call as quantum mechanics or quantum science. So this actually gave a new basic rules at that time, which governed the physical reality and which was different from what was understood as classical physics. And in fact, the whole century, the last century, has spent a lot of time in understanding the basic aspects of matter, the interaction of light with matter, the properties of matter, the properties of light. And it was a conceptual revolution at that way, which actually led to many applications also. So if you see nowadays, you are using smartphones, you are using computers. In fact, the basic of all these are semiconductor components which are being realized, and that actually made things to happen in a very, very smaller scale. Otherwise, things were very large in size. And not only that, there was also things like there are things like medical devices like MRIs and nuclear energies, which are also because of this first quantum revolution, which actually we now call as quantum technology or quantum 1.0. Two more devices which came up during the evolution of these during the last century, they were the laser and the transistors and ICs. Lasers have contributed significantly to the world in almost all domains, in almost all areas, including industries, academia, research, everywhere. And also transistors played a very important role, and now integrated circuits in developing all these kind of electronic devices which you see all around us. So this was all because of the first quantum revolution. Now in this century, we are expecting much more than what is being done. In fact, if you see, there are in this slide that there are several kind of technologies which you must have heard at some point of time. The names must be familiar to you. These are the new kind of technologies which are coming up. They are the ones which are again due to the quantum physics or quantum mechanics, and in fact they are called the second quantum revolution, because here the goal is much more. Here we are not just saying that okay, we will make one more device. We are trying to customize devices. We are trying to use to control the existing science by for making disruptive technologies where we provide our own design and serve our own purpose. And you must be knowing that quantum computers are being developed with different type of designs, where the goal is to make very high computational capability. Similarly, these are long term applications, because quantum computers are being built over last 10-15 years, and we expect that it will again take another 10 years or so to finally come up with these kind of technologies. But there are also some technologies which are short scale or short term, such as quantum communication. There are already significant applications of quantum communication. People have demonstrated quantum cryptography, or in fact quantum teleportation kind of basic principles. And also they are using quantum entanglement to enrich or to improve their devices. And in between there are some medium term technologies which are parallelly being developed, and they have some specific use cases. For example, people are working toward metrology, that is measurement, which is either in the form of quantum imaging, where you can see the objects by imaging it, or you can sense the objects by the sensors, so that you can get sensors which are way more powerful than what are available with classical technologies. And then we know about microwave radars, which can detect airplanes or any airborne objects. Similarly, one can develop much more higher version or highly efficient version of those radars using quantum technologies, which can even detect the stealth objects, stealth aircrafts. And also quantum control and quantum simulations are coming. So basically a whole plethora of technologies are being developed with different type of uh, bases, or different type of existing technologies, such as people are using ions, people are using photons, people are using superconducting qubits for developing these technologies. So the motivation of developing these technologies comes by various ways. One of them, which I mentioned already, that people try to make things miniaturized or compact. You know that nearly 50-60 years before, when the classical computers were developed, they were of the size of the room you are sitting. So one operation was taking days basically to complete. But then the goal was to develop them smaller and smaller in size, and today you know that your watch is already having a computer which is much more powerful than what was there nearly 50 years before. So we are making things smaller and miniaturized. We are increasing the density of components within those sizes, given sizes. Then essentially we are making macro objects to micro objects. And you know that when we move from micro domain to micro domains, the classical physics no longer exists with smaller sizes like nano or pico or even femto sizes, and one needs to invoke quantum physics or quantum principles to understand the interaction of or the behavior of the objects of the micro sizes or micro objects. So this is one of the reason that quantum principles invariably come into requirement as we make things smaller or miniaturized. The second thing is that we have a promise that whatever has been developed so far, which has shown that quantum can offer vastly improved performance compared to classical. And this is why one of the goal is to develop things or technologies as a quantum based technology. And many complex systems which are not controllable in a classical manner, in fact quantum technologies can allow us to organize and control those. For example, if you can make a quantum computer, you can basically model the nature. You can model billions or trillions of atoms together, molecules together, which is not possible, or this amount of calculation is not possible with classical or supercomputers even nowadays. So many such kind of technologies which are coming up during the last decade. We have already seen quantum computers are being built. People are talking about 1,000 qubit quantum computers. There are many key players, such as we have Google, IBM, IonQ, Intel. They all are coming with multi-qubit processors, and the goal is essentially to make systems which are having the computational capability orders of magnitude higher than what classical computer or supercomputers as of now can give you. And they can be used in applications where such kind of tremendous data processing required. For example, nowadays we talk about artificial intelligence. So if you want to really have voluminous of data and we want to such large volume to be processed, then quantum computers can be really advantageous. Quantum sensors and metrology is coming in a big way again. I am showing a picture of LIGO, which is Laser Interferometer Gravitational Wave Observatory in US. And this is an interferometer. And the idea of this is to detect gravitational waves. In fact, it was the first such kind of sensitive device that it could detect a gravitational wave nearly 10 years before. And now many astrophysical phenomena are being detected. So the goal is to enhance its sensitivity further and further, and you cannot make every time a new large interferometer again. So with existing devices, one thing what one can do, that one can use quantum principles here as well. So you see a red plot here, which is basically called quantum noise, or it is called squeezed states of light. So this has been implemented in this advanced LIGO Plus, and they have shown that by doing that, you could actually decrease its you could actually increase its sensitivity, or you could go further down in the sensitivity by 2 to 3 times. So we can expect many more astrophysical events to be detected by the same detector in coming days, which has been improved by this quantum attribute. And similarly, other kind of sensors are being developed. The third and very important is quantum communication, and quantum key distribution is one application of quantum communication. So here, as I mentioned, with quantum computers, you can make very powerful algorithms, very powerful devices which can basically process the data very fast. So you can also break the codes, which security codes, or you can guess some number very fast because of its high computational capability. So existing all classical communication which is using those kind of principles will basically be broken if quantum computers come up. So you need a solution now which can also sustain when quantum computers are around. And that solution itself uses quantum principles. It is called quantum key distribution. And China has been a world leader in several domains of all these technologies. Quantum communication is one of them, where they have demonstrated satellite based quantum communication for more than 1,000 kilometers. And in this talk I will more focus on quantum communication as we go along. So basically, we are not doing quantum mechanics anymore. We are further to that, and we are doing quantum engineering now, where we are using quantum physics with other kind of engineering to make quantum devices. Now, in communication, if you see, there are news every now and then about the security breaking the codes using quantum computers. So these are two such news I am showing you. One left one says that there are some new kind of attacks which are coming, called harvest now decrypt later kind of attacks, where the hackers are storing the information which is available and waiting for the quantum computer. And if such computer comes up in near future, they will use it to break your codes, so your information is not secure. And similarly, China had already demonstrated a military grade encryption was broken by a quantum computer. And that is something which is very alarming for others, because these informations are in fact quite classified. And if they are coming, that means that either they have already done it or they are doing way more than what is actually on public domain. So we need quantum security, the one which cannot be broken by such kind of existing quantum computers, and it is a need of the hour basically. Now, quantum communication, if you see, there are two ways you can do that. You can use the existing optical fibers. Optical fibers are those glass strands which we use for our telecommunication. In fact, nowadays every house is connected with some sort of fiber communication for broadband. Establishments are connected with optical fiber by which they can send the data. And here we are talking about quantum communication using that kind of data, that kind of fiber. So this is one way to do that. There are challenges in fiber-based communication because there are given losses in per kilometer of fiber. Say it is 0.2 dB, 0.25 dB per kilometer kind of losses. So as you go for longer distances, these losses accumulate, and ultimately they are so high that you could not transmit any signal, especially when we are talking about few photons in quantum domain. In one way to go for long distances is to use another kind of communication, which is called satellite based communication. And here, in fact, one variant of satellite based communication is also free space communication. So in free space communication, we typically try to communicate between two line of sight points in a straight manner, in a straight line of sight distance. And you can go for several tens of kilometers if you could align your system up to that. But ultimately, since the earth is having a shape which is round, you cannot go straight for long distances, because your signal will actually will no longer be aligned. It will go away. It will no longer remain straight. Then the solution is to use an external objects, that is a satellite, where you use two ground stations, one to basically uplink to the satellite, and the other way you can downlink to the satellite. So that way you can use a satellite which is also a line of sight for one of the ground stations at a time, and that way it can be also used for long distance communication. In fact, what China has done was one example. I will talk about that later on, that how in the second part maybe, that how China has achieved this kind of communication by using a quantum satellite. And this is another picture how they have used recently another kind of communication, where they actually use both ground stations seeing the satellite somewhere in the center, and they both could downlink the information from the satellite. And that way you could actually connect the two ground stations directly by the satellite at one time. You need not to wait for the satellite at different times. And this can also be basically useful for those areas where quantum entanglement is used. And I will talk about quantum entanglement, where I will explain what is this geometry and how it is used. In fact, people use fibers also for long distance communication, and one of the goals are to use a hybrid communication, where the satellite communication or free space communication can be combined with fiber communication, so that you could have end mile connectivity to each and every user. Every user cannot have a ground station, every user cannot have a free space connection, but you can still have a fiber connection at some places. So a joint activity essentially would be required, where both of them can be used. Now, quantum communication, if you see, security is a very important aspect, and this quantum key distribution is directly linked with security. And that's why there are many key players which are willing to utilize this opportunity to use this quantum security. So you can see that there are people who are mainly this mobile and payment systems, where security is of more concern. They are the main users. Then there are users from the data centers, because they are also dealing with very important data. The telecom, the government, the military, everywhere quantum communication is quite an important area. And a large amount of market value is expected by 2030 in terms of US dollar 20 billion. And this is really one of the area where markets are really very much dependent on the security. uh, in fact, these quantum technologies are not standalone technology. Every technology requires a lot of enabling technologies to realize. I have given an example of quantum communication or quantum key distribution. So the moment I say quantum key distribution, I am basically using and not only quantum sources like photon sources, where one provider can provide us those sources, somebody can provide us the detectors, somebody can provide us the QRNG, quantum random number generators, or QKD products. And then since many of these detectors require cooling, you need cryosystems, you need a lot of sensors, softwares, and all these basically make a single ecosystem. So all these technologies are equally required to develop or to realize quantum technologies. Since many of these technologies are very crucial for a country, they are a national treasure. and that's why they are denied in nature. No country is going to sell many of these technologies if they have developed it to other countries. And this is why every country comes with its own plan of developing their indigenous quantum technologies. You see that every country which are developed or which are toward being developed, they all are using some sort of national mission to develop their technologies. India has come up with its own mission, which is called National Quantum Mission. Let me give you just one slide on that. I am sure you must have heard about that, that there are four verticals on National Quantum Mission. And our goal here is to work on quantum communication, which is one of the verticals, important verticals. And I would be happy if you would be interested in working together with us in this national effort of developing quantum communication devices. Now, let me briefly give you the idea what kind of quantum technologies in communication we are working with. So, we work with free space quantum technologies, where basically the goal is to do QKD with entanglement based protocols and also to do quantum imaging. One of our works are toward fiber based quantum technologies, where we want to be telecom compliant, use both uh, entanglement and non entanglement based protocols, and also to develop quantum networks. We have also uh, one area where we use single and entangled photons development, where we want to be high rate, high purity, and high brightness. And also with some colleagues in material science, we are trying to develop superconducting nanowire single photon detectors, which are very efficient detectors for detecting those signal like single and entangled photons for doing quantum key distribution. So in this today's talk, I will focus on free space quantum technology, what we are doing, and also in between, I will tell you about how we develop single and entangled photons and how we detect them. Okay, so this is the plan of talk to some extent. So I will focus first that what is the need of quantum cryptography or quantum key distribution. What are the basics of this quantum key distribution? How do one go for free space based quantum key distribution? And further, if one want to scale to satellite, what are the ways to do that? And what are the challenges in communication and more or less in quantum technologies? And finally, I would summarize my presentation. Okay, so let us go further and try to discuss about the properties of quantum objects we are talking about, which are important for quantum, for realizing these niche quantum technologies. We know that unlike classical objects, which can certainly be at a particular position, these quantum objects have superposition states. That means that they are they have states which are basically at many places at the same time, and it's the measurement which decides that where this particular state would be finally projected. Let me give you an example. If we take classical objects, we typically define them with bits. Bits means we have one as a given voltage level, which is a defined voltage level, zero as another defined voltage level, or it can be, say for example, up spin and down spin. So these are the standard examples of classical bits. Now if I ask you what is this diagonal spin, then you would similarly say that it is an error, because there is no definition of this in these scenarios. We have one and zeros, there is nothing defined as half of that or a particular direction of that. But for quantum things, this actually is also a particular state. It is called a superposition state, which is a superposition of this up and down, and that makes a diagonal. So you can have actually infinite set of such states which can be present, where some combination of one is superposing with some combination of zero, provided that the norm remains as one. So these are the specific properties of superposition states or qubits which actually make them that much powerful. They work as wave and particles. So this is another important aspect, because when we talk about classical objects, we say that okay, a wave is a wave which can actually be propagating, and it has an amplitude, it is a continuous object. Whereas particles are discrete objects, they can have a well-defined position and a well-defined size or one well defined structure, and these two are just opposite of each other. But quantum mechanically this is not true, because at the very small level, at the elementary particle level, these wave and particle definitions basically go away, and any quantum object can behave as wave, it can also behave as particle. It is depending on the observation how you basically look that object. So it has both kind of features. And one important theorem which comes for the quantum objects is called no cloning theorem. And no cloning theorem is something which says that you cannot perfectly clone or copy a quantum object. Classically, we know that if I ask you to copy or to clone a page of information, you can go to a photocopy machine and you can make hundreds of copies of that identical information. But quantum mechanically, it is not allowed. If you have a quantum state which is unknown to you, when you try to measure it or you try to copy it, you have to make a measurement, and that projects the state into one of the possible outcomes. So you cannot perfectly copy a quantum object, and this is the reason that we can use these quantum objects for security applications such as quantum communication applications. The combination of these three, qubit, superposition, and interference, can offer you many applications. One of them is quantum computer. I will not go into the details of what kind of quantum computers are being developed, but I will just tell in connection with quantum communication that there are different type of qubits which are being formed, which can be either superconducting, spin, ions, or even photons. And all these are basically used to develop what we call quantum computers, and such computers will have several functionalities as shown in this slide, and it will be a big threat to existing security system due to these kind of efficient computers if they are built. And the moment they are built, there will be a big threat to our high level communication, which is being done over a very secure channel through either military or in diplomacy or everywhere basically. And we need to make that very secure, and one way to do that is use quantum security. So I will now explain what is this cryptography or quantum cryptography and how it works. So in general, we all know that cryptography is a way to disguise the information. So if I want to transmit my message to somebody else, obviously if I transmit it as I am speaking, then anybody else can understand it. I have to encrypt it in some way so that it is restricted to the unintended recipients, but only be understood or only be uh, responded by the person who understands it, and that will be a intended recipient, the one who really wants to get the information. And in case of quantum cryptography, as I mentioned that, and I think I repeatedly mentioned it, that many of those security solutions which are available classically are with the help of mathematical problems or with the help of some complex solution which is not solvable as of now with classical computers, but a quantum computer can easily solve it. And once it does it, and also one thing to be noted here that in case of classical cryptography, the key transmission can be passively monitored by any eavesdropper without giving any alert to the legitimate users, which is forbidden in case of quantum objects, because once they are measured, they inform about their measurement, and that way any user can know that there has been already somebody who has tried to measure those quantum states, and that is a eavesdropper in this scenario. So these problems are solved very easily with quantum computers. So as of now, there are two ways by which you can send and receive the secure information. One is called symmetric encryption. Symmetric, as the name says, that both sender and receiver can use the same key to encrypt and decrypt a message. So the sender uses the transmitter uses its text combined with the key, sends it to the receiver, and receiver has already that key available, and that uses the same key to decrypt that message. And an example of that is the one-time pad or one-time password which you use. So basically, when you make a credit card transaction, you receive a 6-digit or 8-digit password, and this is basically the key for authentication, which is also available exactly in the same manner with the other party who wants to make the payment. So the moment you correctly enter it, it matches with that key, and that makes the transaction. So here, the secure communication channel which we use is a trusted courier for distributing the key. But in general, it is very difficult to solve the problem of key distribution, because if I want to communicate somebody with America, the question comes how I will use the same key which the American counterpart is using. How we all both have distributed the key, because any usurper can also come in between while the distribution of the key, and it will know all about the information. So this key distribution problem is very, very important. However, in case of classical systems, as of now, people use trusted couriers for that. It's a very fast technique, because since we are using the same key, the resources are very, very less used, very low usage is there, and it's very secure, because every time you can change the key, and you use a new one-time password, so nobody can basically guess it so fast. However, if you want to make it more secure, clearly just by adding the digits in the password would not be a solution. An example is that if I give you a 100-digit OTP by your phone and ask you to enter it, it will be very difficult for you, though it will be very secure. So in order to increase the security, especially when we are using internet or digital transactions, there is something called asymmetric encryption which is used. In case of asymmetric encryption, there is a public key which is accessible to all of the senders, and there is a private key which is accessible only the one who wants to respond. So now there are two keys, and the length of the keys could be any size. They can be very, very long as well. And the solution, and nobody can guess those keys, because the solution typically is in the form of computational complexity. That means that if I give you uh, uh, product of large prime numbers and I ask you to factorize them, current computers of having a 100-digit number will take probably years to solve the problem, whereas a quantum computer can solve it in a fraction of second, because it has some well-known algorithms such as Shor's algorithm, which can break them very, very fast. So all these asymmetric encryption, which is the backbone of internet and the digital world, would go away as the quantum computer comes in. And here is where we need to provide some solution in the form of the cryptography, which is coming from quantum domain. So quantum key distribution is a way to communicate with absolute security in the presence of any eavesdropper, and one can use a common random string, that is the what we call the key. And we use the principles of quantum physics that I already mentioned you, that any eavesdropper who tried to intercept and measure the optical signal in between actually changes the quantum state. And as the quantum state changes, the Bob will immediately know, once it looks into the quantum state, that somebody has already either intercepted it or measured it. And that way they can be alerted themselves that the Eve is present into the system. To be more precise, this communication is typically done using photons, which are photonic qubits. So you have a quantum channel where you send photons, and as I mentioned, this can be either optical fiber, or it can be free space, or it can be satellite. You use a classical channel through which you interact between Alice and Bob, and they set up or they talk and give some outcome, that okay, whether they are getting errors which are prescribed within the limits, or they are beyond the limits. And the information which they are sending through the photons or photonic qubits, it is encoded using some property of the photon. So as I have shown here, you can either use a polarization qubit, that means you can use horizontal polarization, vertical polarization, and its superposition, Or you can use orbital angular momentum, where you have L minus L or its superposition. And then many times people use time bins, that is early arrival, late arrival, and its superposition. So using this, the information can be transmitted using quantum bits, and then you have also classical information, and both together can make a complete system of quantum key distribution. And as I mentioned about fiber, you can use off-the-shelf components so that you can use classical communication together with quantum communication, and you can use different kind of schemes by which you can do this communication, which can be either called prepare and measure schemes, or they are called entanglement based scheme, which I will explain in a bit. Now, so when we talk about satellite based communication, there are actually worldwide several missions where people have tried to send satellites or send objects into the space. And a snapshot of those missions is shown in this slide. So you can see that there are successful missions, like China has sent Messias satellite, which has been the most successful. Before that, they used balloons so that they could see that whether in a smaller scale, if such communication can be done. Then they went for a longer scale. Canada is trying some sort of satellite communication. Europe is also trying both geostationary as well as lower Earth orbit satellites. Singapore and Europe together are also trying on CubeSats. They are like small nanocubes or microcube, small satellites which are not a complete satellite, but they can still be used for communication. And then there are some countries which have also tried unmanned air vehicles like UAVs or even other kind of satellites. So this is the typical picture, like how in general people are trying to use satellites for such communication. Now I mentioned about QKD, so let me go a bit detail about the protocols, which kind of protocols can be used. So I already explained you that you have Alice, you have Bob. Alice is typically the transmitter or sender, Bob is the receiver, and then you have EU, which is eavesdropping. It is eavesdropping into a quantum channel, but it can eavesdrop even the sender and receiver as well. There is no such restriction given to EU that it cannot be attacking. There are protocols which are based on two categories. You can use a set of rules or protocols either using single photons. In this case, they are called either BB84. This is Bennett and Bessel in 1984 proposed the first such protocol. Then there are other protocols like B92, decoy state BB84, and then there are phase-based protocols like DPS, different distributed phase shift, and coherent one-way protocols. And there are entanglement-based protocols like ECAT 91 or BBM 92 protocols. In all these protocols, two things which are of much concern are either key rate or quantum bit error rate. Quantum bit error rate or QBER is a parameter which tells you that out of 100 photons which were sent from Alice to Bob, how many were wrongly received at Bob. And this is shown in terms of percentage. For example, if 5% of the photons have been incorrectly received, you say that the QBER is 5%. And then due to the QBER, since your data becomes spoiled, you would like to remove them which are incorrect. So finally you decide that during your communication of keys, what type of rate you achieve. One is raw is the one which is achieved with error, and then there is secure key rate, which is after removing all the errors and all the problems associated with the communication, and these are called raw rate as well as secure key rate. Now, the way the communication can be done, we have different modes by which you can do. For example, there are two type of systems as of now available. One are using discrete variables. That means they are countable kind of basis sets such as single photons, which you can detect or count, and you define error here, the QBER which I mentioned, and you can go for long distances, and you can use technologies like detectors, which are single photon detectors, to detect these photons. But there are also another type of schemes which are coming up, which are not using single photons, but they are using waves like coherent states, which are called continuous variable states. One uses instead of using single photon detectors or photon counting, one uses homodyne detectors. And this homodyning gives you both the amplitude of the signal and the phase of the signal. The losses basically enhance the noise. So if you see more noise, you know that, okay, there is an eavesdropper in the system. And in fact, since these are continuous variable systems, you have much more bandwidth compared to discrete variables. So you can go with very high rates. But the distances are limited. Typically, they are few hundreds of kilometers, not more than that. And this is the limitation here. But this limitation is basically compensated by the high key rate. So if you want a metropolitan kind of network, continuous variable kind of systems are also a solution. And error correction is a problem here because you don't know how to correct the errors because the data is voluminous. A lot of information is encoded there, but still there are ways people are trying to figure out that how post-processing could be made. Now, in general, if we take any quantum key distribution system, we need to use some classical post-processing techniques to reduce the error, to detect the error, and at the same time to amplify the privacy of the system. So I will not go into the detail. It is more about a classical object, classical things, but it tells you that how we can basically use classical methods such as authentication, by which you authenticate the parties, whether they are really the ones which are supposed to make communication or we are communicating to some adversary. That is done by authentication. And then you define the parameters such as QBAR and key rate. Then you remove those by shifting. You reconcile and figure out that, okay, this information, these are the bits which has been wrongly received, so can we simply remove them and try to improve the privacy of the system, because while doing this process some information might have received by the eavesdropper also, which you want to remove, and that gives you the final key. The security which we are interested, as I mentioned earlier also, is unconditional security, because you don't want your system to be, attacked by the eavesdropper and you make a more powerful system in the next go. Quantum computers would be one of the most powerful devices, and if you can make a system which cannot be broken by quantum computer, you basically stop all other kind of hacking attempts, because all other attempts are basically low or less in intensity compared to what quantum computers would be giving. And the three kind of information you would like to secure: one is the confidentiality. That means the information is confidential only to the legitimate party, it is not open to public. The information as it is sent is received, it has not changed, that is called integrity. And also the information which has been sent has really authentic, it's not that this has been either shared or modified because of certain attempts. Now, I already mentioned you about no cloning theorem, let me not repeat it again, but this is important that when you do this, use the no cloning theorem, it is only when we are talking about there is unknown state or there is only one photon at a time. If by any chance instead of a single photon you send two photons, say I send two photons together, then the eavesdropper can actually take out one photon there, it is called a beam splitter attack, and that photon will be with Eve, which it can use to get the information. Whereas Bob will still receive the other photon, and Bob will have no idea that the photon has been already with the eavesdropper or with the adversary. So, no cloning theorem, though protects the quantum states, multiple copies of quantum states once they are available, or multi-photon signal is available, then it cannot do much. And one has to be really use systems which are not producing multi-photons but only restricted to single photons. Then only the communication would be very, very secure. I think I will stop here and maybe we can have some time for question answer and then maybe some break afterwards.
Yes. So there are a few questions, only two questions basically. So any applications built on quantum entanglement? So any applications built on quantum
Yes,
entanglement?
yes. So in the second part, I will show you how we can use quantum entanglement for quantum communication. So far I am only focusing on the basics, but in the second part I will show you that the free space communication we have been doing, it is actually based on quantum entanglement, and it can provide much more security than what is available with non entanglement based systems, and that's why it is very, very important.
Second question is based on use cases for drone-based QKD.
Okay, so I think this is more on application side. This question would have been in the second part, much easier to understand for others, but still I can answer it. So when we talk about satellite based communication, we are talking about a perpetual network. We say, okay, the satellite will come and you will make communication at two ground stations or multi ground stations, which are always there. It's not easy to move the ground stations. But suppose in a scenario like there is a war suddenly happening in a city and you want to make a local network, then you cannot put ground stations immediately for satellite communication. So in that situation, you can do is you can put a network of drones which will basically be communicated to some movable ground station or some movable object like a car, for example, which is having a transmitter or a receiver, and then a local kind of network can be set up. This is called on demand quantum network. So drone based systems can be very useful for on demand quantum network, or in war type of scenario where you do not have a perpetual network but you develop the network just for a interim time when you need it, and then you destroy the communication. So there drones are very useful.
Okay,
Sorry.
there is one more question. Where is the detector exactly for satellite-based communication? Because if it is satellite, then how to send signal from satellite to receiver? Probably this would be answered in the next session.
Yes, yes, because I will come to satellite portion in the next time. So I
Got
think those will be already answered there to some extent.
Right. So we can move on to the next one is for asymmetric distribution. What is the general example?
Yeah, all the communication which we are doing, for example, when I am opening a web page, I am there is already something happening at the backside, at the back end, and this all is happening with asymmetric communication only. So there is a server, there is a client. Client asks server to open a particular content. Before doing that, they basically try to secure the channel, and that securing the channel happens with asymmetric keys only. So they send a, for example, a public key, then the public key data is opened. Suppose let me give you the example in a way. Suppose I'm a server and somebody wants to contact me. So the computer which wants to contact me will have a public key. It will send to me, and since I have a private key, I will be able to access the data which is being sent by them, and opening that data will tell me, okay, this is the particular thing, and then I will make a secure channel using this communication, and the keys will be shared. And once both of us have shared the keys, we can use those keys to basically do all other communication afterwards. So this is an example of the standard communication which is happening, and most of the places this is based on this asymmetric communication only.
Okay, next question. I'm not sure. Probably the question is how quantum communication advantage. Probably he's asking how it can be made more efficient using LLM JEPA tuning.
What is that? LLM? Then what is the next
JEPA,
thing?
JEPA, JEPA, all capitals. JEPA, tuning.
I don't know what it is. Basically, it is some specific algorithm in LLM. I'm not much aware about these large
Sure.
language models, so I don't know. I mean, what it is. If
Okay.
it is more
Okay. So we.
specified, then probably I can answer it. Yeah.
Okay. So. Uh, Next question is what is the difference between the satellite QKD and free space China satellite QKD? Of course, there is no China satellite. Oh, so satellite QKD and satellite QKD and free space satellite QKD.
No, so satellite QKD and so free space, there is nothing free space satellite QKD. It's only satellite QKD. It is also in free space. Maybe in the next part, I will talk about satellite QKD. Then I will explain it with more detail.
Uh, the next question is, let's say we generate 2-qubit entanglement, same ket 00, ket 11 over square root 2. Say we have to distribute these 2-qubit as one to Ellis and one to Bob. Is it possible using optical cables? Also, if electrons are used in this entanglement, then it's not possible to have far distances. Is it right?
Okay, so what I understand from you that they are asking that can we do it with electrons? The answer is that with electrons probably yes, but if you are using normal wires by which there are there are infinite electrons in normal wires, so how you will distinguish between the correct electrons which are actually carrying the entanglement? And this is why when we are sending these particles we are using optical fibers, and we try to use a specific wavelength of photons which we can later on distinguish and take out those photons which are carrying quantum entanglement. So unless you know that which electrons or which photons are having those entangled information, you cannot do the communication. And especially in this case it is still not possible with electrons, because when the electric current is flowing on a wire, it's not that every electron is reaching from point A to point B. The drift velocity of electrons is very small, it's a few centimeter per second only, but it is the phase of the electrons which decides that. It's like a pipe filled with water, you fill more water from one side and the other side the similar amount of water will come out. So it's not the same water content which is going from one side will reach the other side of the pipe, which can be for example 1 kilometer long. So for entanglement you need those qubits which are actually carrying the entanglement, and if they are not there then the information is not received basically.
So next question is, to what extent we can accept the key with some errors?
Yeah, so that also I will tell you depending on the protocols. There are protocols typically where the key threshold is error threshold is 11%. So if you are less than 11 then you are secure. If you are more than 11 then you assume that somebody has tried to intercept your system and that's why the error has increased, and you simply discard the information. You actually basically start again.
Okay. So there is a clarification on the previous question related to LLM, but probably I don't think it's in the scope of your talk, but we can still discuss the question, which is which type of role joint embedding predictive architecture of recent December 2025 overshadows LLMs in quantum communication?
Oh, no, I'm sorry, I'm not aware about this 2025 thing.
Okay. So we can move on to the next one, which is, are there any active quantum entanglement networks in the world? If yes, how long are such networks?
No, there is no active that way. People sometimes do some demonstration, but then it is not active further. There are networks which are active, but they are not based on entanglement. They are based on prepare and measure kind of scenario. Entanglement is very difficult to generate, and it is more difficult to sustain for longer times. And this is why normally people do not make entanglement based networks, and they are also very new. In fact, an entanglement based network is not a very old thing, it's quite new, and that's why there are still developments happening to make them more efficient, more long distance, and error free.
Okay. Next question again is probably related to machine learning. I'll just read out and probably we can ignore this, which is, can we apply TensorFlow quantum on quantum communication?
See, we can do many things, but all this is again simulation or data processing based. It's not experimentally realizable thing. Quantum technologies utilize this measurement dependent outcome. That means you observe the state, you measure it, and it projects into some outcome. Unless you do that physically, you can simulate it always, but your simulations will not give the same result which experimentally you should obtain. And this is the exact difference between learning quantum physics by theory and doing it experimentally.
Okay. And the last question in, what is different between quantum and classical channel on physical aspects?
See, the fibers we use for classical channel, we try to use the same for quantum channel, but sometimes the fibers may be very lossy. So for example, which I mentioned you, that typical losses in fibers is a few zero point 0.2 dB, 0.25 dB per kilometer. But sometimes that loss, because of certain reasons, can be 0.5 dB or 0.6 dB per kilometer as well, 2 or 3 times more. Classically, it is not a problem, because if you lose the information, you can put an amplifier or a repeater, and you can again get the information. That's you can retrieve the information. Quantum mechanically, you cannot do so, because as I mentioned, you cannot copy the information. So the moment you add something, it will change the nature of the quantum system or the quantum state. So you cannot put any amplifier or any sort of those repeaters which classically you can put. And this is the reason that we have to make our channel low loss, low dispersion, so that you could go for longer distances. And the same actually is valid for free space communication also, because classically you can always amplify it. Quantum mechanically, if you have many losses due to fog, due to pollution, or due to, for example, this atmospheric turbulence, you lose the information. Quantum mechanically, you cannot retrieve it back.
Okay. So can we can take break for I mean, you may decide the time, sir.
Now you can tell me what is the typical practice, because we have spent 1 hour so far.
So 5 to 10 minutes break we can take.
Yeah, so we can make some break, and then I will continue from there. Okay.
So we can we'll meet at 4:10.
Yeah.
Probably you can directly start the session without me initiating anything.
Okay, fine. In 10 minutes we will start. Okay, thank
Yeah,
you.
sure.
So, good afternoon once again. So, we had already discussed about several aspects of QKD, some basics and some advanced aspects while we were discussing the question answer session. Now, let me go back and try to give you some practical applications, some implementations which people have made so far, and also some aspects associated with quantum entanglement, because it is one of the very important key ingredient which can be used to secure the communication way more than what it is actually with single photons. So what are the sources of quantum key distribution? So there are several type of sources, but we can start with the most basic one. We all have seen laser beams. We have seen laser pointers, for example, by which you can get laser beams. So one easy way to make a single photon source would be to attenuate the laser beam. So if I can use a very heavy attenuator, a sheet, a pile of glass plates, for example, each of the glass plate will reduce the intensity, and ultimately the intensity would be so low that you cannot see it by naked eyes. You can still see it by detectors, very efficient detectors, and if I have sufficiently attenuated it, then even those detectors will only be see it at some times, like out of 1 second you will get probably few detections there, and there we are basically approaching to single photon level. So this is a easier single photon source which you can implement, you can make in a lab, you can make in a house, for example. What we measure here is the multi-photon, which is a very important aspect. And unfortunately, with case of single photon, with case of this laser, the distribution which is Poissonian doesn't give you a it doesn't get rid of multi-photons basically. So irrespective of whatever be the attenuation, how much you reduce it, you will still get sometimes many photons, sometimes one photon. However, you can use the laser as pulse laser, and that way you can work at megahertz or even hundreds of megahertz kind of rates. So high rate single photon sources can be developed, and they can be perfectly indistinguishable as well, because you can always make them in a way that you any two photons would not look very different. What we measure is the second order correlation function. I don't know if I have an expression for that. No, not here. So this is basically telling you that whether the photons are always far from each other or they are coming together. If the photons are only single photons, like I am showing here, these two photons, if all are these two photons where there are no joint photons, this quantity would give you 0. But here you see that you have sometimes two photons together, sometimes even four photons club, three photons clubs together. So this is a very random event. And in case of random events, when photons are coming like that, the G2 parameter is always 1. And this is the signature of a Poissonian source, that G2 is always 1. So such kind of sources can be developed. And as I mentioned, that you can use a beam splitter based two detector based scheme where you look for the correlations in photons coming. If it is single photon only, then one detector will click, the other one will not click, and you will get G2 equal to 0. But since it's a random event, you expect that at a time both detectors will click, and that's why you get a G2 of 1. Now this is the Poissonian distribution which I mentioned. What it means is that depending on the mean photon number mu, which is basically shown here as n bar, you can see that what is the probability of getting 0 photons, 1 photon, and many photons. So you see that as I decrease, that I attenuate the laser, I get more lesser and lesser mean photon. The probability of getting 0 photons becomes more and more. That means you will have no photons into the pulse most of the time. For example, for point 1 mu, you will have 90% time no photons, 9% time you will have only single photons, but at least 1% time you will have multiphotons also. And this multiphoton, as I mentioned, can be easily dissipted by photon number splitting attack. Normally these kind of sources, weak coherent pulse sources, sometimes are very they offer some sort of compromising the QKD solutions when you are using it for very secure applications. But if security is not very high, then you can use these as one of the sources, and it is not a problem. You can easily do that. Now, the other kind of sources which one can use are called single photon sources used on based on some phenomena or some process, and one of the process is called spontaneous parametric down conversion. So what happens in that process, which I will explain in the later, is that you can basically shine a laser beam and you can get a correlated photons at the output. These correlated photons can be used as a single photon. For example, you see here that a intense laser beam is striking on a nonlinear crystal, and you get these photons which are always correlated. You get 2 photon, 4 photon, these always in pairs. And then you know that if there is a photon, there is a photon as well. If I use a detector here and I know a click here, which means 1 photon is detected, I immediately know that its counterpart is also there in the second arm, and that can be used for any application. So that kind of single photon source can be realized by using the process of SPDC, or spontaneous parametric down conversion. The photons, there are other ways by which you can make those photons, which are either decays, ion decays, or diamond vacancies, or even atomic transitions, and this is how they look like. So you'll have very less, G2 is very, very small, which is very close to zero. That means you have mostly single photons, and sometimes you have 2 photons. So this is there, the probability of attacks becomes extremely low, because you have hardly any double photons there. Or you can see here that you have all single photons. So these kind of sources can be developed. In fact, many a times you are not interested probably in communication, but more on seeing the basic aspects or basic experiments. In those cases, these weak coherent pulse sources which I showed you are sufficient by attenuating a laser. So I'm showing you one small experiment where I am using such laser. I am passing, I am attenuating it so that I am getting single photons. The photons are very less in number. Say in 1 second, I get few tens of photons, and they are separated by several nanoseconds or even microseconds. That means the distance between photons, if you multiply this with the speed of light, you will get several kilometers. So photons are very, very far from each other, and they are falling on a double slit, and I am looking into the screen. Now, in normal circumstances, we know that if it is a particle, it is showing a particle behavior, each of these slit should give one peak at the other side, because it's like throwing balls out of a window. So you will get two piles in front of two windows. But here it's a microscopic particle. It's a single photon, which is a quantum offset. It doesn't behave just as a particle, but it behaves as a wave as well. So if I don't disturb the system, I should be able to get an interference pattern. And I'm showing you this by using this experiment, where the screen is shown here as this left side black region, where these white dots are basically already having some detection of photons. So any detection here will be coming as a white dot, which is basically a single photon. And as of now, these are all dark counts or dark photons, because there is no signal, but still they are spurious photon counts coming from the ambience. So I'm running this video to show you that how the experiment runs. So you see that I am now looking into the screen basically with time, and these are all single photons falling on the screen, which are essentially behaving like a particle. But you see that they are actually being detected at designated places. Some of them are showing as maximas, some of them are showing as minimas. So if I run this significantly long, you see that with time, if I run it and do it fast, you will be able to see some lines as interference patterns. And these are the interference pattern associated to single photons. So single photons basically, which are actually, as per the terminology of particle and wave, behaving as a particle, but when it passes through a double slit, it is, since there is no observation made, it is actually passing through both the slits at the same time, interfering with itself and giving you an interference pattern. And this is how the single photon interference is achieved. So you see that there is no way to know the which path information the photon takes. So photons are behaving like a wave, and they interfere with themselves and give you interference pattern. So this is a very interesting experiment which can be used to show students that how a single photon behaves as a particle. Now let's go back further and try to see how a quantum key distribution system looks like. So we have now, you see upside I have, let me go back. Upside I have this source, which is typically some quantum source, which can be a laser, which is controlled by a FPGA board so that I can make it pulsing. I have some sort of basis selection here, which is in case of normal QKD experiments, polarization basis. So we can have horizontal or vertical or a diagonal basis. I use some quantum channel, which is a free space channel typically. And then after that, after passing through that quantum channel, I again couple my beam to a fiber, which is basically using a basis selector again, which is again controlled by FPGA and synchronized with the transmitter, so that at the same with the same RF frequency, I can control my detection part. And finally, I have these detectors as single photon detectors. So I use a random basis at the transmitter and a basis at the receiver, by which I can control what is being detected and in what basis it is being detected. So I can have key rates and Q bar as I mentioned earlier, and I can measure these values from my experiment. So this is a typical experiment which one can do, and I will show later on that how we do those experiments using this kind of scheme. Now I mentioned you about this spontaneous parametric down conversion. Let me give you some more practical aspects of that. So if I use a camera, which is a single photon camera, this is the same camera by which I detected those interferences in single photons. If I use and I shine this nonlinear crystal with a pump and look into the profile of these photons, this is how the photon profile looks like. So we get sometimes this peak in the center, which is called a collinear geometry, or I can get a ring like thing which is called a non-collinear geometry. And if a type 2 scenario where both the rings coming out similar to here are having different polarization, say the left one is horizontal one, the right one is vertical one, and there are cross sections where these two rings are cutting each other, and this cross section is the point at which we do not know what the polarization is. The polarization can be coming from this ring, so it is horizontal, this ring it is vertical. But what I know that at a moment if I measure here and it is horizontal, I immediately know that the remaining vertical will be here. So you see that the information of the system is not complete to you. You only know a priori that there are two polarizations, but which one you will detect, the information is not known. But we know that there is a 50% probability that I will detect either horizontal or vertical. So the information globally, if I see, I have only a picture that tells you that the photons will have two polarizations and you can detect one of them at one position. However, the moment you detect it, there is 100% surety you have that the other one will be opposite of that, because they are coming from different opposite polarizations. So this strange property is called quantum entanglement, and it has been not just a so far it has been not just a theoretical media, but it is an experimental fact. And 2022 Nobel Prize has been actually given to the people who have proposed about quantum entanglement and also detected quantum entanglement. So let me give you an example of a quantum entanglement based system. So let's say this is a state which has two polarizations, horizontal and vertical. A is horizontal, then B is vertical, and if B is horizontal, A is vertical, and happening this combination has a probability of 50. That means 50% time I will get horizontal vertical combination and 50% time vertical horizontal combination. So if I have a source like this and it gives you these two photons in two directions, and I take these photons very different distances from each other, so it can be in different galaxies, it can be large distances, like say one photon is detected in India, other one in US, so that we don't have any idea what the other photon is doing. And I use two polarization selectors which tell me about the polarization of the photons. And if it is transmitted, I know it is one polarization. If it is reflected, I know it is another polarization. So the moment the first one transmits, Say in India, I measure it and I get a transmission, I immediately know that my counterpart in US has a vertical polarization. And the reason is because they are built in a way that the whole system is a complete system. It's not just my system is a partial part of the whole system. The complete system contains my photon with my counterpart photon in US. So if one is transmitted, the other one will be reflected. If I make another measurement and my photon is reflected, which is a vertical polarization, I immediately know that the photon in US must have transmitted is horizontal polarization. So this kind of information, irrespective of whatever be the distance and whatever be the measuring equipment, I will always get opposite correlations. And this is the beauty of quantum entanglement. So you know that we are talking about now of those kind of systems which are one-to-one connected, one-to-one entangled, and no other photon is entangled with that photon. If I am entangled with a photon of my friend in some place in the universe, then other photons, whoever else is having, is not sharing that entanglement. So my entanglement is not only unique, it's a private as well. So it can be used for secure applications. And that we will show you that the QKD which we do, we can have QKD using entanglement and we can have QKD without entanglement. They are called prepare and measure systems, where Alice prepares a quantum state, send to Bob, and then they do the communication. Whereas in case of entanglement, as I mentioned, I have an entangled photon source. It gives you two photons. One photon is detected by Alice, one photon by Bob, and then they set up the communication. So these are some features and some limitations of these kind of systems. For example, currently, since prepare and measure systems come from classical technologies, they have advanced significantly compared to new kind of systems coming from quantum technology. Entanglement based systems are still in its nascent stage. They are still being developed. That's why the efficiencies are not high. The rates are typically lower compared to what prepare and measure systems can offer you. However, the good thing is that they can lead to many those applications. Uh, they uh, they can have, for example, if you see here, trusted node free kind of architecture can be developed, which is not there in the previous case. And trusted node free architecture is something like that uh, that you don't want any. If I want to communicate from my place to say some place in which is 100 kilometers away, I don't want any intermediary in between who could who could be used to transmit that information in case I don't have an efficient 100-kilometer long system. Classically, people do it, I mean, with prepare and measure systems, people do it with trusted nodes. But here, as I told you, that these trusted nodes are, though they are secured, secure nodes, the security is physical. And if somebody could trespass that security, they can get the keys. So they will basically compromise the system. Whereas trusted node free architecture requires quantum entanglement. In quantum entanglement, the source which is producing the keys, even if a hacker takes the source, as long as it is giving you entangled photons, you can always do a secure communication. You don't care whether the source is with you or with hacker or with somebody else. And also QKD using entanglement can offer many advanced benefits which are not possible in the realm of prepare and measure systems. For example, you can do quantum teleportation, you can do quantum repeaters, and you can also do quantum swapping and quantum metrology. So there are several benefits of QKD based on entanglement. So what I will do, that I will talk about both schemes one by one so that I could give you some idea. So decoy state protocol is a protocol which is based on prepare and measure systems. Normally, when we send photons, many a times it is possible that an eavesdropper can store that photon and release another photon with similar properties in case to the Bob. So in order to avoid that, one can use decoy states. Decoy states are decoys, as the decoys they use in armed forces. These are the ones which are purposely placed photons having two photon signals or higher or lower information than what the actual single state signal photon has, and they are used to detect any eavesdropping or detecting any sort of information, information trespassing by the eavesdropper. So you see that standard BB84 protocol, which is here, can go up to securely up to 55 kilometers or so. Whereas when you introduce decoys into the system, you can go for very long distances, up to 150 kilometers. So decoys, using decoys into the system basically makes the communication longer, and it can go for large distances as well. The other kind of protocol we use is called BBM92 protocol, and this is using the entanglement which I told you. So entanglement can be generated and distributed, and using those entangled photons you can do a communication. Let me give you an example how you do that. So we have an entangled photon source which is with some user Charlie. We are sending one photon to Alice, one photon to Bob. Alice has two bases, horizontal, vertical, and diagonal and anti-diagonal, which are basically like horizontal, vertical is 0 degree and 90 degree polarizations, and 45 degree and minus 45 degree polarizations are these diagonal and anti-diagonal polarizations, and this is true for both sides. Now, when the entangled photons are being detected randomly, this beam splitter randomly sends these photons from either, when it is receiving it, it sends either to this or this. Similarly, this photon sends this to this. It is a random sampling. So you see that you have randomly kept different bases. Alice sometimes put diagonal bases, Bob puts plus bases, and so on and so forth. So the measurement of the same photon in different bases would be different. You see the outcomes will be random. And if you convert these diagonal and vertical to encoded photons, you will get zeros and ones, which is shown here. However, you only look into those cases when Alice and Bob have used the same basis. You see, this one is the same basis, this one is the same basis, this one is also the same basis. So only those green ones are the same basis, whereas the wrong bases are simply rejected. The reason being that when you put wrong basis, you are basically making a partial measurement, and that can lead to any random result, and you do not trust on those results. And now you see that when you have looked into that, since the photons were anti-correlated, H and V, you convert one of them to make it correlated. So you make them 0 to 1, similarly 0 to 1, this 1 to 0, and so on and so forth. And then you look into the security by you testing the errors, and that gives you finally the key. So you see that you can use entangled photons for quantum secure communication, and this is the protocol BBM92 which is used for this communication. So an example of doing this entanglement based communication is this free space communication made for the first time in 2007 by a group in Europe, and this was basically done between two islands close to Europe called La Palma and Tenerife, and the distance between these islands was 144 kilometers. You can see here. In fact, they were using the existing observatories of these two places, these two islands. This is the observatory picture of this Tenerife, and this is the transmitter which was at La Palma. So the distance is 144 kilometers, which is quite amazing, because after that nobody could achieve this long distance in direct communication so far. This was the only experiment which has achieved it, and they used sea because it was very peaceful in sea. There was no atmospheric turbulence, there was no pollution, no fog or nothing. The atmosphere was quite transmittive, and that's why they could go for very long distances. And this is the picture of how they have used a laser with some crystal to produce entanglement, send one photon this way, received here with a telescope. The other photon was detected itself in the same place, and when it was detected, it was measured through the another bell test setup, and then finally they used a classical channel to communicate whether they were able to do that. And these are the results. So they have in fact made systems by which they can basically control the tracking of this of those beams, so that the telescope and the source always remain aligned. So this is the tracking beam. When they track the beam, they are perfectly aligned, otherwise they basically misalign themselves. And this is the coincidences which they have achieved for about 221 seconds. And this is the visibility of at the receiver. Then you see that the visibilities are more than 90%, which tells you that you have very high quality of entanglement. And let me tell you that the measurement of entanglement is dealt by an inequality which is called CHSH inequality, which is also called S parameter. And the value should be more than 2. The maximum value is 2.8. And they were able to achieve a value 2.5, which is very high, showing a high quality of entanglement. Now, similar kind of experiments very recently we did at IIT Delhi, and I have presented it in one of the conferences here. So this is the experiment. You must have heard about it, though I will explain it a bit. So in India, so far the distances achieved in free space communication were very low, that is about less than 300 meters. So we decided to go for longer distances, say 1 kilometer or more. And within IIT Delhi campus, where I am currently working, the distance maximum we can go is only this, because the campus is within the city, and the actual distance which we can achieve between two big buildings is limited by this within the campus. So what we did, that we made an entangled photon source. We measure one photon within the end station of one building, send the other photon through a telescope to the atmospheric channel, and received by a telescope other side, and then again the photon was detected with a Bell test here. The two buildings which are shown here are there. This is a research park building which is within IIT Delhi one side, and there is a ground of IIT Delhi, and the other side is the main building. The main limitations of this kind of communication are that the atmospheric turbulence affects a lot, especially in Delhi where pollution is very high. So what we did, that we looked into the beams, that how they are jittery when the pollution or the air is flowing. So you can see that how in the other side of the building, how the beams look like when they are passing through the optical turbulence. So these are the main challenges associated with free space communication, that how you will basically reduce those kind of atmospheric effects, and would be able to detect the photons. So these are one of the challenges associated with this. But in any case, we were able to demonstrate. You can see, you might have seen this picture some time back. So this is the night view of this experiment. This is the Alice side, which is over this building. You can see the building here. The bob is the other side of the building, which is not visible because this line of sight is only up to here, and the building is somewhere here. This is the telescope which is being used to detect those photons, and this is the transmitter over which the photons have been sent. This is a green beam, which is a guiding beam, which is sometimes also called a beacon beam. It is used to guide the two transmitters and receivers so that they are aligned in the line of sight, and then you remove this beam and put a quantum beam which is invisible to human eye. And that's why we typically show this green beam here as a beacon beam. These are some of the results associated with the measurement. So you can get a QBER of less than 7% in some cases, up to less than 10%, depending on what kind of coincidence windows we are selecting. So we could get a key rate of 242 bits per second when the QBER was 7%. And if I want a higher key rate, I have to compromise with the QBER. And the S parameter was about 2.4 in all the cases. So the goal of this experiment was to test the communication, whether it is only the sea type situations or hill type situations where the weather is calm, you can do the communication, or you can do it in very noisy, very polluted, or very foggy kind of atmospheres as well. Because this particular was during the summer, there was no fog, but there was still some haze and a lot of pollution as well. However, we were still able to get a good quantum entanglement along with a key rate and QBER. So if you want to go into the more details, there is a YouTube video where I had an interview with Sunset TV, where I discussed about several aspects of this experiment. So you are welcome to visit this particular website for details. Now let's come to satellite-based communication. So far we are doing free space communication, as I mentioned. Now, free space communication is line of sight. You can go up to two distances which are visible from one to another. Now, because of the curvature of Earth, you cannot go very long in the straight line path. Your path will become curved. And since the light cannot go to curved path, they cannot be remaining line of sight, and the light will be blocked by some obstacle on the way. So the only way to do that now is basically to use a satellite somewhere which is far from the earth, but it is visible to both the ground stations. So you can uplink with one ground station where the satellite can see the signal and it can downlink to the other one. So that way you can use satellite as a node where you can do the communication between any two end stations. Now there are different geometries by which you can do that. For example, there are geometries which are called uplinking geometries. In this case, the source is in the ground and the detector is at the satellite, and you uplink from ground to the satellite detector. Many times you put your source in the satellite, you put a ground station where the detectors are in the ground station, and then it is a downlinking scenario. And sometimes you do a double downlinking because you can put an entangled photon source which is giving you two photons. So you have two detectors in the ground, and you can detect, both can detect these two things, two photons, and make communication among themselves. Typically entanglement based scenario, you can say. And then you can also make a constellation of satellite where you put many satellites together. The ground stations can talk to individual satellites which are on their view, whereas the satellites themselves are, always seeing each other in the space, so they can always communicate between them. And that way you can make a inter-satellite link or a constellation of satellites. So currently, these are some of the scenarios where people are working in. This scenario has also been tested by China, and they have been very successful in that. And this is a scenario which is possibly in next 10 years time when people will be making extra constellations, so that they will have availability of signals and they will be able to secure everything with quantum communication. This I have already explained you, so let me not go back to it again. Now let us look into how China has been able to do different kind of communication experiments. So this is a satellite to ground quantum communication which used a Messias satellite, and it was a sun synchronous orbit with an altitude of 500 kilometers. And it was done in 2014-15. In fact, it was published in 2017. Satellite was launched earlier, but the communication was done within next 1 year. And before, they have used hot air balloons. So these are some of the components. You can get that information on this paper. So this is the photon source they have used. This is not an entangled photon source, but a preparant major source. However, the receiver this side, and they have shown that this is the typical trajectory of the satellite where the distances can be very large, like 1200, when the satellite is either rising or setting. And then at the daytime, when it is at the head top, the distances were 600 kilometers. And depending on those distances, the losses were different. So you can see that you could get a loss up to uh, this is the rate. First, we can talk about the rates, and then we will talk to the loss. So the rates you can achieve for this shorter distance would be higher because the losses are less, whereas for the longer distance, the losses would be more. So the key rates would be smaller. In fact, there is almost zero key rate at large distances, and the QBER was surprisingly very low. That was less than even 2% in most of the cases. And these are the losses where they compare this distance of 1200 kilometer with a fiber based distance which they could have achieved with fiber. And you can see there is a difference of order of magnitude 20 between what fiber losses would have been incurred and what satellite is giving to you. So it means that satellite is 10 raised to power 20 times better in terms of losses compared to a fiber. And that's why for long distances it is the best candidate for quantum communication. In the same satellite, they used an entangled photon source also. This is a typical source using periodically poled KTP, and they have shown that with this they were able to go do demonstrate the quantum entanglement. And this is the transmitter for the entangled photon source. This is the receiver for the entangled photon source. And now you can see that their attenuation with distance was increasing significantly, going up to 42 dB, and they could measure the entangled photons within from the satellite to the ground station very effectively. And they could also make the bell test. For example, you can see here, these are the QBERs which were achieved for entangled photon source, which were less than 10%. That means they were almost entangled. And this is the key rate which was achieved, which is in terms of coincidences, and they were getting up to 600-700 coincidences in 10 seconds. In fact, they have also shown that if the satellite goes through different places on Earth and can be tracked in different cities, say Beijing and Vienna, they could make an intercontinental video call where they can send the keys from uplinking from Beijing, going all the way to Vienna, and then downlink by the Vienna again by the satellite. And that way the same key was shared between the two parties, and they can use that key to make a communication. And this was done in 2017. So I think this gives you a fairly good picture about how satellite based communication is happening. Now let me go back and talk you about the networks, because satellite is one way to do it for long distances, but if you want to do it household or within the cities, you still need to use fiber. So in China, for example, they have developed a network of 5,000 kilometers, which is called China Quantum Backbone, where they have connected their fiber connection to different cities, and ultimately with a ground stations with the fiber as well. And earlier in Tokyo, for example, they have demonstrated a fiber based network nearly 15 years before. And such kind of networks are indeed required, because ultimately when you have quantum computers, say these are the computers or quantum end nodes which are available, you need to securely communicate between those computers. And the only way to communicate between computers which are working with qubits is to use a quantum communication, because classical communication is only limited to bits, which is currently being done with the internet using the classical computers. So you need quantum computers. If you develop quantum computers, you need quantum communication to communicate securely between them. And you use quantum interconnect such as quantum repeaters, switches, and quantum channels such as fiber and free space. And that kind of network together will be what we call quantum internet, which will be a complementary or a supplement to the existing classical internet, because there are many tasks which are out of reach with classical internet which can be done with quantum internet, and remaining tasks can be performed with the classical internet. So let me also inform you that under National Quantum Mission, we are running a project called Towards Trusted Node-Free Hybrid Quantum Secure Communication Network. It is short form called Tehqiqat, where we have IIT Delhi as a lead institute, and there are other partner institutes as well. So we are trying to set up a network connecting 4 cities, UP, Delhi, Haryana, and Uttarakhand, which is basically a fiber network with 6 nodes. But at 2 places, at IIT Delhi and IIT Roorkee, we are connecting it with a free space node as well. So you can see that IIT Delhi, we have already a free space connection of about 1 kilometer, half kilometer to 1 kilometer, and similar network we are aiming to build at IIT Roorkee, and that way it will be a hybrid communication which will include both free space and fiber based communication for understanding different aspects of quantum networks and quantum secure communication. And I believe that this will work as a cornerstone for future quantum internet, where such smaller networks, regional networks, can be connected together. And this kind of network, multi-node network, can be used for many applications. For example, you can do computing, distributed sensing. You can do quantum applications such as teleportation, internet, and repeaters. You can do position verification kind of aspects. Position verification is a very important area, where you can actually verify the position of a server which is actually connecting to you. And currently, you know that a lot of scamming is happening digitally, where you do not know which server, which country they are connecting to you, and that way nobody can catch them as well. But if you have this quantum position verification, which can be possible with multi-node quantum networks, you can actually fail the attempts of the scammers. So if you want to know more about that, I have a TED talk recently on scamming and how quantum position verification or quantum networks can actually avoid these things and catch the eavesdropper using the quantum traits or quantum features. So I would invite you to have a look into this talk if you want to go into more details of quantum use of quantum technology for making a scammer free world. uh, if you want to go further more on quantum communication in free space, you can develop quantum radars. Quantum radars, as I mentioned, are very efficient radars compared with the microwave radars so far available. You can use an entangled photon source. You have signal and Adler two beams. One beam uses as a reference beam and other one is as an object beam, and that way you can trace the object very, very easily. So there are ways where people are trying to develop them for many applications, especially for military applications, wherein when a stealth aircraft or a invisible drones or something can be detected using quantum entanglement. And in fact, it's not just quantum communication or quantum computing. There are many other applications of quantum technology which are coming up. Probably I don't have time to go into detail of that. So they include several applications in magnetometry, gravitational sensing, and all that, which can be useful together with communication, internet, quantum internet, and quantum computers. So I would also like to mention that we have been recently coming up with some, since we have worked a lot toward a proof of concept or technologies on quantum communication. Now we are coming up with some translational products on those technologies, which are not only the elements of quantum networks, but also single and entangled photon sources. You can see that these are the prototypes of single and entangled photon sources, which we have recently developed. And one of our main focus is to develop experimental kits for UG and PG labs, where the students can not only do hands-on training, but can also have a lot of skill development. And let me give you an example what kind of kits we are developing. So this is, for example, a kit which is a 4-in-1 kind of experimental kit, where you can not only start with the basic of Young's double slit experiment, you can do a single photon Young's double slit experiment as well, which I just explained to you. You can use the effect of polarization on this interference, and finally you can make a quantum eraser, where you can show that the moment you try to observe these quantum states, the interference disappears and it becomes just two peaks, and in otherwise circumstances where you do not disturb the system, it remains as an interference. So these kind of kits are currently being developed. So I would be happy to discuss more in case you have any comments on these directions. Finally, let me conclude by saying that slow quantum communication is a very, very advanced technology now. Still, there are some open challenges, which are not only because when we treat it as a theoretical system, we have many assumptions. But in real world, these assumptions uh, cannot be directly translated as the real system. So you can have a gap between what you have assumed and what you have finally delivered, and that gap leads to some security loopholes, and that opens attempts for people to hack those quantum systems. So in order to nullify that, one needs to really assess their quantum systems and come up with the loopholes, which can be actually improved by putting some countermeasures, and that way quantum hacking kind of attempts can be stopped. We need to develop several long distance communication networks, and one of the problems is that there are no repeaters and memories as of now available, but still people are trying to work on those direction, and I expect that very soon we will have some usable repeaters and memories available. We need to work at very high rates if we want to provide keys with the rate the data communication is happening, and for that need of quantum interconnects is very, very important. Hybrid networks, as I mentioned, is one of the area where we need to really look into, because finally the systems would include both free space and fiber parts, and both have to be handled together. And QKD requires fiber, so one needs to coexist classical communication with quantum communication. And many times people are not very much trusting on quantum systems, assuming that they may not be very reliable. So this public trust and adoption needs to be improved. And if you are interested in some initial documentary kind of thing, where you could, if you are a beginner and want to understand what quantum technologies can provide you, so this is a video which we made in collaboration with Vigyan Prasar, DST. So it is available in YouTube and also in India Science Channel, so you are welcome to look into that. So I summarize that we discussed about quantum revolutions and quantum technologies initially. I told you about some aspects of protocols and experiments in QKD. And finally, what is the need of QKD, and what are the challenges associated with that. So I'm thankful to the funding agencies, DRDO, DST, National Quantum Mission, and the Institute of Eminence, IIT Delhi, for their support, and also all these smiling faces on your screen who have been actually working in the lab for realizing all these technologies. So I would like to acknowledge their efforts as well. So thank you very much. And if you have any questions, I'll be happy to answer them. So are there any questions? I see there are some messages, but I don't have a track of what messages at all are there. So if somebody of you can read them, then I would be happy to answer.
Just a second. So I'll read out these questions. So there are few questions. So there was this question which was posted, what you mean by beams you displayed? What you mean by
No,
beams? It was
uh,
asked, I'm almost 20, probably
no,
related to
so
some
when
slide.
the person who asked the question explain where we talked about beams, because ultimately when we are what we are dealing is these whether it is single photon or entangled photon, they are propagating in free space, and they can only propagate if they propagate like a light beam. Beam means it's a collection of it's a collection of light rays which are focused and propagating in a specific direction. If it is not focused or if it is propagating randomly, then it will not be able to reach the target. So we have to make them in the form of some concentrated beam of light in order to propagate up to the receiver basically. So these we call typically light beams.
Okay. The next question is, can you please clarify on wave and particle nature of photon?
Oh, so this is, I think, one of the classical questions associated with, it's not only photons, but any quantum object essentially can be described by a wave function. It's neither wave nor a particle, but it's a wave function. And the outcome of this wave function is in the form of some probability. So it's basically mathematically, it is psi star psi we call typically, and it's the probability. So quantum physics relies on this probability only. So any particle, we classically we talk about particles and waves. We say that okay, some objects are looking like particles, they are very very definite, they cannot flow, so we call them particles, they are discrete natures. Some are waves which are continuous, so we put in a different box of waves, and that way we categorize things as particle and waves. But quantum mechanically there is no such distinction, because at the microscopic level they all mix together. So there is no such distinction that you can say okay, this is particle, this is wave. Both waves and particle together are behaving in the same way. This is the wave function only, which gives you both these natures depending on the observer who is looking into. In my experiment, for example, I showed you that if you want to see the particle nature, you have to observe it as a particle, and the way to do that is to know the trajectory of the particle, that where it is going. And the moment in a double slit you try to do that, that which slit the particle or the photon is passing, you will get only two peaks, because you reduce the outcome as a particle nature. If you don't want to see the particle nature, you just close your eyes and don't observe it, it will show you the wave nature where it is present everywhere. So both are the essential part of quantum world basically.
Okay. The next question is probably more. I'm not sure whether it should be addressed to you or not, but then the candidate is asking for what are the postdoc opportunities in a combination of field of let's say quantum computing, quantum communication, and AI.
Well, I mean, they are they are I mean, AI is slightly different, but quantum computing and quantum communication are related areas. The postdoc opportunities are everywhere. You can just look into the, I told you about the quantum mission, national quantum mission. If you go to their websites, they have open opportunities available. You can also look into the, you can find the people you are interested in, and then you can directly contact them. As of now, you see that there are many fundings are coming, so of course people require trained or skilled manpower for contributing in those areas. So you should be in contact with those people, and then probably you will have a chance to go there.
All right. So the next question is how the channel fading effect can be analyzed in FSO QKD.
FSOQKD, what is that? Channel fading? What is that channel?
The channel fading effect can be analyzed in FSQKD, free
So
space optics probe.
free space optical QKD, which we discussed, if the channel is fading, you can always see the outcome in the form of key rate. You can see that how the key rate is fluctuating, whether it is decreasing, whether it is increasing, or what is happening to it. And typically with time, since the channel becomes more, the kind of, because if you do for long distance communication, it will be affected by the atmospheric effects, and that way it will be reflected in the form of the losses in the photons, and that will be in the form of the key rate, basically how it is decreasing.
Okay. The next question is some textbooks for quantum communication.
There are no such direct textbooks on communication as of now. As of I know, they are only on quantum optics, quantum, in general, quantum mechanics, and all that. Quantum communication is a very specific area, and I don't think any very well-known textbook as of now is available for communication only. But you can go to some standard books which are available. For example, there are books by Gary and Knight. For example, it is on quantum optics, introductory quantum optics. And there are books by other researchers. In fact, there are books by Indian researchers as well, some of the elementary books. My suggestion would be you start with a specific focus on learning quantum optics or quantum photonics first, and a lot of aspects of quantum communication, because we are using photons, are covered in quantum optics itself. Only what you do afterwards is engineering part, which is more of experimental in nature, and it will not be available in any books. You have to do it in the labs, basically.
All right. So thank you very much, sir, for taking time to for being an expert speaker in this FDP, and patiently answering all the queries of the participants. And I hope the participants have gained the immense experimental